All right, so let's get started on today's class. So what we're going to do today is we're going to go over a little bit of what we need to know for the rest of the semester. Basically, we're going to introduce the basic approach that we're going to be using to try to understand behavior and cognition for the rest of the semester. So this will be the introduction to cognitive psychology. So this is going to talk about what it is that there we go. This is going to be talking about what it is that we consider thinking to be, cognition to be. So in order to study anything, you need to be able to model it. You need to be able to represent it somehow. And same thing with our cognition. So what is it that we're doing when we're thinking? How can we, as psychologists, think about thinking so that we can get insights and make progress in understanding human cognition? So we're going to take a look at the one of the main hypotheses behind cognitive psychology, which is the physical symbol system hypothesis. But we're also going to start off first a little bit more basically by taking a look at what it means to actually understand something. So if you say to yourself, I want to understand cognition, or if you say to yourself, I want to understand depression, or if you say to yourself, I want to understand anything, what does it mean to say that, yes, we now have a full understanding of it? We'll check that out as well. So we are going to take a look at cognition, the idea that when we're doing cognition, it's much like when a computer is crunching data. So we're going to take a look at the information in, manipulation, information out approach. And all of that is going to be so that we can set the stage for what's coming up in the rest of the semester. All right, so we're going to be, again, focusing on what is thinking, what is cognition, and how can we as psychologists understand what's going on. And then we're going to take those approaches and we're going to apply it to a very simple task that we all know how to do, which is letter recognition. And we're going to take a look at different attempts at explaining letter recognition, including one attempt that hypothesized that we have representations in our mind that work very much like demons in rooms talking to each other. And while it might sound ludicrous to think that we have a theory that basically posits that we have little demons running around in our head in order to help us recognize alphabet letters, we're going to see that it actually is one of the best explanations for how letter recognition actually occurs. All right, so we're going to talk today about the information processing approach. We're going to take a look at models of the mind. So why do we use models at all? And what do we mean by models of the mind? We're going to take a look at Marr's tri-level hypothesis, and I'll let you know amongst his 3 levels where we're going to be spending most of our time here in cognitive psychology. And then we'll talk about the idea of what a representation actually is. We'll get clear on that so there's no confusion going ahead. And then finally, we'll illustrate all these principles with an example of letter recognition, where we take a look at how letters are recognized using both the template model and the Pandemonium model. All right, but first, when we're looking at thinking, in order to, again, study any sort of behavior, you need a way of conceptualizing it. You need a way of understanding it. So when behaviorists started analyzing learning, and they started analyzing how humans and animals learn, they had to identify units of behavior that they could analyze, such as how many times does a mouse press the bar. So that was something that was measurable. That was a concept that they understood. Learning was conceptualized as increases in the frequency with which the bar is pressed. So they had an idea of how to tackle this subject of behavior. But for cognitive psychology, we need the same sort of beginning. We need to know, how can we conceptualize what thinking is, right? This mysterious behavior that goes on, covertly in our mind. How can we think about this in a way that will give us insights into this aspect of human behavior. So the way that the basic approach that's going to be used in cognitive psychology, and this might seem familiar because cognitive psychology has spread to encompass almost all psychology. So you might be a developmentalist, you might be an abnormal psychologist, you might be in personality psychology, but you'll probably use the cognitive psychology approach to understanding that area of psychology. And for a cognitive psychologist, human cognition can be thought of as information processing. It can be thought of as taking information in, doing something to it, and then spitting out information. So the mind that we have is an information processing system. And that's what we're trying to understand. How does our mind work? How does our mind do that thing that it does, which we label as cognition? So this information processing system, it takes in information in one form, and then it processes it into another form, and then that is the output that we have evidence of. So we know something's going in, we know something's coming out, and we as psychologists try to figure out what happened in between in order to get that output. So to give you an example, here we have a mind, and let's say that information starts coming into this mind. So we have information inputs that are coming in. So we got two vertical lines coming in as inputs. And we got two diagonal lines coming in as inputs. And we got two horizontal lines coming in as inputs. And we got two other diagonal lines going the other way coming in as inputs. So that's the information that is being input into this mind. Let's say that in addition to that information, we also have location information. So we had orientation of the lines coming in. Let's say that we also have location information, so that the two vertical lines are in those particular locations. The diagonal lines are in that location, those two. The horizontal lines are in those two locations. The other diagonal lines are in those two locations. So we have additional information coming in for spatial location. And then finally, we have one last piece of information coming in, which is color. So we have the information that this other information is to be bound together with color, and your mind processes this, puts it all together, and ends up with this cognition. It ends up with this perception. And then when you add that information processing, which occurs in your mind, you add that to memory, things that you've learned, information that you have stored in your mind, ready for access. It combines those two processes, and it knows that you're looking at a stop sign, and it knows that if you are driving, now is your time to hit the brake, and behavior occurs because of this information processing. So all this information came in, the mind processed it somehow, and then the information came out in a new form, a new cognition, a new representation. So that's the approach that we're going to use to try to understand human cognition and human behavior. And it works very much like your mind is a computer. So one of the big analogies that is used in cognitive psychology is that your mind is a computer. Cognition is like running a program, running software on hardware. And basically, we are at a time right now where that approach is starting to pay off massive dividends. So as our understanding of our own cognition increased, we were actually able to build better and better computers. And that's why now we have AI exploding the way that it is, and we have cars that can actually drive. You know, we have bots on social media that can actually pass as, you know, human individuals. So all of that came from an understanding of how human cognition actually operates. All right, so we have the information processing approach. We're also going to lean very heavily on models of the mind. So we're going to be looking at specifically the mind. We're not talking about the brain. We're talking about the mind. So what constitutes the mind differs between different people. All right, there used to be an idea that your mind was basically your brain. That has been supplanted by the idea that your mind includes your brain and also your body. Your body is actually part of what your cognitive apparatus is, and that's known as embodied cognition. There's also the idea that the world is actually part of your mind. So if anybody ever forgot their cell phone at home and realized that your ability to do cognitive work plummeted that day, you'll know that you do store and use some cognitive resources as part of your mind external to yourself. That's known as embedded cognition. So that's what we're going to be looking at. We're going to be looking at the mind, not the brain. We're going to be looking at the mind. And we're going to need models of the mind to represent how our mind actually works. So we're going to take a look at some of the advantages of models. And the big one, the first one that we're going to take a look at, is the fact that they are simpler. So your mind is probably one of the most complex things that exists in our universe. So when we attempt to understand it, we need to scale it back to simpler models of what the mind is in order to be able to even make that initial approach to try to understand what is going on. So as an example, let's say that you were trying to understand geography. This is a satellite picture of North America. If you were trying to understand geography, countries, you wanted to know where Canada was, you wanted to know where the United States was, this would actually be very, very complicated to use. Right? So if I was to ask you, where's the border between Canada and the United States, and you look here, it would be difficult to figure this out by looking at a satellite photo of what the Earth actually looks like. But if we had a model, all of a sudden it gets a little bit simpler, right? So this is not what the Earth actually looks like. This is what it looks like. This is a model. And it's a little bit simpler. And now you can, if you knew a little bit about it before, kind of find out where that border is between Canada and the United States. If we take it a step back and simplify that model even further, then all of a sudden it becomes readily apparent. And you're like, oh, okay, boom, right there, very, very clear where that border is. So the same way that simplified versions of the Earth can help us understand certain things about geography, simplified versions of our mind, simplified models of our mind can help us understand this vastly complicated thing that we somehow implement using our nerves and bodies and environment. So we're going to use models because they're simpler, and we're also going to use models because they serve as a starting point and they suggest questions to ask that you might not have thought to ask previous to those models. So these models can be used to understand an information processing approach, both by being simpler and also by allowing you to ask the right questions. They push you in the right directions. They enable you to get insights that you might have missed in the more complicated version of the actual system. So we're going to use models to understand an information processing system, specifically your mind. We're going to use models to understand your mind. So we're going to talk about ways that your mind might work, ways that your mind might be, but they are going to be simplified versions, oftentimes only tackling a specific area of our cognition. But again, this is our way of understanding this massively complex system known as our mind. All right, any questions so far on what we've covered? All right, so how are we going to understand this? Well, we're going to understand this, and we're going to illustrate our approach using Marr's tri-level hypothesis. So Marr was a researcher, he was a psychologist, he was in perception. He made massive contributions to the field of perception. He died way young. I believe he died in his 30s, unfortunately. But he did make a massive contribution also to just a general idea of what it constitutes to understand something, for us to understand something in psychology. And it was called Marr's tri-level hypothesis. So he posited that to fully understand this information processing system, this mind that we're trying to get a handle on, you have to understand it at three distinct levels of analysis. So once you say, oh, psychology understands the mind, we figured out the mind, we can explain cognition, what it means is that you can explain cognition at 3 levels of analysis. Once you have that, you have the complete picture. So what are the levels? The first level is a computational level, and this is the problem that's faced in computational terms. For our purposes, what this means is that this is a listing of everything that humans can do with their cognition. So human beings can alphabetize lists. That is put in here in the computational level. Human beings can recognize faces. That's put in there at the computational level. Human beings can walk around a room and navigate without bumping into things. That's put there into the computational level. So anything that humans can do goes into the first level, the computational level. And this is basically a listing of everything that we need to explain. So this is one of the easier levels to get a grasp on, because literally it's just almost, you can think of it as a catalog of what can we do, and then it's up to us to try to explain it. But first things first, we have to know what is it that we're trying to explain, what is it that we can do. The second level is the representational level. And the representational level is strategies, models, theories, representation that might be used to do the list that we have in the computational level. So here we have, for example, alphabetized lists. At the representational level, we might say, well, how? What's a strategy that people use to alphabetize lists? What's a strategy that your mind might use to alphabetize lists? So for example, does your mind, take the first word and then decide if the second word goes before or after it? Then does it take the third word and just go down until it finds where it should go on the list? The fourth word, go down until it finds where it should go on the list. Is that the representation? Or does it take the entire list and for every pair, if they're in the correct alphabetical order, it leaves it alone. If they're not, it flips them and then just goes through n-1 times, however large the list is, and alphabetizes it in that way. So what are the strategies that might be used in order to accomplish the things that we can do? So that's the second level of understanding. At that point, we still don't have a full understanding of how cognition works. And the last part is the implementation level. And the implementation level is, how is this strategy actually done in a physical entity? So if you're a computer programmer, how do you put this strategy into an actual computer program? If you're a psychologist trying to understand the human mind, the implementation level is, how does our brain, our body, and perhaps the world actually physically make this strategy possible, put this strategy into action? So we are going to camp out in this course mostly at the representational level. This is where we're going to stay for the vast majority of this course. The implementational level, this is neuropsychology. So psychology about how do your neurons work, what's in different areas of your brain, what's the functional, what does area F1 do in your brain? That's the implementation level. And we're going to stick here at the representational level. This might inform the implementation level, but this allows us to just focus on the strategies, on the models, without worrying how does our brain actually do these models. And that is an important portion of understanding the entire information processing approach that our mind uses. All right, so don't be surprised if you do not see any discussion of neurons and brain areas and brain lesions in this course, single cell recordings. That's a behavioral neuroscience, neuropsychology area. That's an important portion, but we are going to stick to the representation level. What are the strategies? What are the models that our mind actually uses. All right, so that representation level, that is an extremely challenging level to understand. And the reason is because any system, ours included, can use a variety of representations in order to represent information. So what representations does the system use? We need to know what processes does it use in order to manipulate those representations. So first off, what are the representations? Second off, how are those representations manipulated? How are they combined? How are they deleted? How are they changed? How are they influencing each other? What happens to these representations when they're in your mind? That is also part of understanding that representational level. All right, so we're going to stay at the representational level. And we've been talking about representations a little bit now without getting into too much of the nitty-gritty of what they are. So let's do that before we go on any further. So when we say representation, what exactly do we mean by representation? So it's got an English meaning to it. It's got an every single day meaning to it, but in cognitive psychology, it means something very specific. So, you might talk about, well, I don't like my representation in government. That's not what we're talking about here. You might say things like, well, there needs to be more minority representation in mainstream media. It's not what we're talking about here. What we're talking about is representation for cognitive psychologists, and that is an internal hypothetical. We don't know if it exists. We hypothesize that it does. It's a theory, but it's an internal symbol that stands in or represents for an external reality. So there's something real in the external world, and in our minds, we have a symbol that stands in for that external thing. So for that stop sign is the external reality. There actually is an external real stop sign when in the external world. So that's the external reality. And those internal symbols that we used as an example, those would be the representation. The internal symbols that are inside our mind. If you're a neuroscientist and you're working at the third level of Marr's tri-level hypothesis, you then have the task of deciding or explaining how are these symbols, these internal symbols, coded in our neurons, right? But that's a different course. So don't get confused about that. Don't wonder where is that part of the explanation. We're not going to be doing that in this course. This is going to be mostly second level. So these are the internal symbols. That's the external reality. And the two of them don't need to look very much like each other. That's another challenge, right? It doesn't have to have a one-to-one correspondence. You could represent this external reality as just a series of orientations, a series of locations, and a color. This looks nothing like this, and yet this could be the internal representation of that external reality. So the challenge comes because any external reality can have a variety of different ways that it's represented. Right? Any cognitive any external reality could be represented by a variety of cognitive symbols. So we have one really great example of this, which is language. So different languages have different words for the same external reality. So there's an external reality out there that people who speak English call dog. There's the same external reality that people who speak French call chien. And people who speak Spanish call perro, right? Same reality, different symbols in language. Same thing for cognitive symbols. So the external reality might be the idea of two, right? There are two fish here. Two is an external reality. Two of something exists in the real world. How do we represent that in internal symbols? Does our mind, and remember, this is our mind, not us, right? Not us as human beings, because we know we communicate the idea of two using this curved line and this straight line here. But does our mind represent two in its mind in this way, using this symbol? Or does it represent it as two individual points, right? Both of these could represent two. Or does it represent it as this, right? And if you understand binary, you'll know that that is the representation for two in binary. So there's a number of different ways to represent something as simple as the idea of two. And as cognitive psychologists, we need to figure out how is that external reality represented in our minds. Mm-hmm.
Are these representations conscious or subconscious? So is this the way that you like think about it consciously, or are the representations sort of like something that we just sort of like it's just there and that's how we process things?
For the most part, it's unconscious.
Okay.
Yep. Cognitive psychology, and that's an excellent question, because one of the biggest kind of underlying challenges in psychology in general is that we have very, very, very little access to what our minds are actually doing. But we kind of feel like we have a lot of access to what our minds are actually doing. And this is something that mainstream people who don't take a psychology course will believe. You know, so one thing that always kind of gets to me, we cover advertising in my psychology of learning class. And if you tell people, well, you know, billions of dollars are paid on commercials every single year, most people will say, yeah, but, you know, advertising doesn't work on me. You know, so let me just open my Coke, put on my Levi jeans, and walk off to my, you know, Honda Accord, right? It works on you. But I never feel like advertising is working on me, right? I've never seen a commercial and said to myself, you know what? I like how much fun they're having at that beach party. I think I'll drink Coke so I have as much fun at my beach parties, right? I've never thought that. What was that?
What does it say about me if I do notice that about myself? I'm like, oh my gosh, I'm totally drawn to this because of that.
Sometimes, yeah, sometimes that does work. But for the most part, you're completely unaware. So there was, and if you want to know kind of just the idea of how to represent information, how important that is in terms of finding an approach that works, one of the first major approaches in psychology history was introspectionism. And introspectionism was the idea that if you trained observers enough, then they could sit there and introspect, think inside about what their cognition is doing. So they would take things like they would give them lemonade, and you would taste it and you would say, that is sweet and sour. Those are the basic units that I'm experiencing. And psychologists spent years running experiments where they used introspection to kind of think inside and say, when I see that door over there, I know it's a rectangle, but I'm perceiving a trapezoid. That's what I'm, perceiving here. That's what they did. And it was decades before they realized it's useless. You have no idea what you're actually processing. So that's a challenge here. I mean, cognitive psychology would be way simpler if we could just say, oh, here's the external reality. Let me look inside my mind. Oh, yeah, I'm using this one. But what we find is that it could be any of these. And it's up to us as psychologists to kind of set up situations that can tell us which one of these it actually is. Mm-hmm. So, again, give you a little bit more of a complicated example. Let's say the external reality. Here we have the United States. We got the difference between Los Angeles, I think Dallas, and New York. And we have the internal symbols. And the internal symbols, they can be very much like external reality, right? So sometimes the internal symbols, there's evidence that the internal symbols we use have the same sort of spatial, physical correspondence to the external reality that they're representing. They look like what it is that they're representing. Sometimes. Other times, those internal symbols don't look at all like what they're representing. So you might represent the external reality of United States geography as just a series of propositions, just a series of statements. Your mind might represent this as Los Angeles to New York, 2,790 miles, New York to Dallas, 1,547 miles. That might be the way that our minds represent this information. And we as psychologists don't know which one of those it is by introspection, by looking inside, but we do know by setting up the experiments that form research psychology. So we do know, or we can figure out which one of these internal symbols is being used by asking somebody, what's the distance between Los Angeles and New York? And if it takes them a long time to figure out the distance between Los Angeles and New York, specifically if it takes them longer to figure out the distance between Los Angeles and New York than it does between Los Angeles and Dallas, that would be evidence that they're using some sort of image internal symbol, because the actual distance on this image between Los Angeles and New York is longer than the actual distance between Los Angeles and Dallas. So if you were to do a reaction time study, for example, and as quick as you can answer Los Angeles to New York, okay, I know how long, how far that is. Los Angeles to Dallas, okay, I'm a lot quicker on that. That would be evidence for this internal symbol. For a proposition representation, there should be no difference, because it takes you exactly the same time to access this proposition as it would take you to access this proposition. So there should be no difference in reaction times. So psychologists will do those studies and make the determination of whether our internal symbol for distances is more like this or is it more like this. And that's, again, why we do that kind of research. All right. So what is a representation? One of the big reasons that we need to know this and come up with the right representation, the correct representation, the representation that we humans actually use, is because these representations will influence the kind of processing that actually can be done. It has huge effects on our behavior, and we already saw this last time in that first class with that train problem. So notice the difference in the output, the behavior that occurs when you represent this as distance. So students that represent this as distance, they will take hours to solve this problem, if at all, if it's even possible for them to do it. Students that represent this as time will take seconds to solve this problem, right? So 100 miles apart, two trains going towards each other at a combined speed of 100 miles per hour. They're going to travel for an hour. Bird is flying 80 miles per hour. It's going to fly 80 miles. It literally takes you under a minute. So representing it in different ways, our minds using different representations can vastly influence what our behavior is, or vastly influence what our possible behavior actually is. Mm-hmm.
Do you think that's is that, I guess, do you find it's based on learning style or things that we've already been exposed to? Because I did the distance one, I don't know, the whole time you went through, I think I was still trying to figure out how much time it takes one train, whatever. Mm-hmm. But what makes some people be able to figure it out one way versus the other?
Well, some representations are more hardwired than others. So some things will be represented the same regardless of how learned or how practiced you are. Practice will actually change your representation sometimes. So there is plasticity in your brain. So for example, if you're a violinist, you'll have more of your cortex actually dedicated to your fingers because you move them around, you practice so much. So more of your neurons will actually be taken up, which means that your representation must have changed if that third level, that implementation, is actually changed. But also what they found when they studied expertise is that as you practice problems, typically higher level problems, your representation of them will change. And there's a study where they did it on physics, and they asked first-year physics students to try to solve a pulley problem, to try to solve an incline problem. So, a block of wood is slid down an incline. There's no friction. How fast is the wood going to be going when it reaches the bottom? And they asked experts, physics professors, to solve those problems. And they used completely different representations. So the students used the representation of distance and angle. What's the angle of the incline? What's the distance that it's going to slide down? Here's the acceleration that it's going to occur. Experts just said, well, the block is this high when it starts. It's going to be at the bottom when it finishes. It's got this much potential energy. That's going to get caused, that's going to cause this much speed. And they're done in a few seconds. So through learning and practice, you can actually change your representations. Another good example of that is if you look at chess experts, they versus chess novices. If you ask chess novices to look at a board and memorize where the pieces are, they will memorize them according, piece by piece. And that's why they'll suck at that, because there's 32 pieces on a chessboard, I believe, if nobody got killed yet. There's 32 pieces on 64 squares. It's hard to figure out where all of those are. That's just beyond anybody's ability. You get a chess expert to try to do that, and they will reproduce much of what was on the board, not because their memory is any better, but because they've changed their representation. So rather than seeing individual pieces, they see different strategies. They see like a weak kingside attack. They see like a bishop knight. I don't play chess, but combination maneuver or whatever. They see the entire board and maybe 3 pieces of info, and then they're just able to reproduce that. So representations can definitely change as you go through practice. But then other representations are very much kind of hardwired, and those tend to be the lower representations. So for example, if you don't have any markers, it's a little harder to improvise. Luckily. All right. So if you studied perception, there's a very famous illusion called the Mueller-Lyer illusion. Should I do those right? Okay. So that's the Mueller-Lyer illusion. And the illusion is that this line here and this line here are actually the same. But these lines here cause the illusion where this one looks to be longer than this one over here. Now, I did my my master's thesis and my PhD thesis on visual perception. I have published numerous articles on visual perspective, on how our visual system represents perspective, on how that influences our perceptual system. So I know a lot about perspective, and I know a lot about vision. I cannot get these two to look the same length to me, because that representation is just hardwired, right? So it doesn't matter how much you know about vision. You might know that these two are the same, right? So usually when I ask this question and I go, which one of these is longer? Is it this one? No hands go up. I go, is it this one? No hands go up, because everybody knows they're the same size. But if I ask which one of these looks longer, I could get somebody who's seeing this for the first time, and I could get Mueller and Lyer, the guys who made these, and both of them will still say, yeah, this one looks longer, because some representations just won't change. All right, so that's what a representation is. Some of them are malleable, some of them are not. Some of them will change over time, some of them won't. But to explain any behavior, we need to ask ourselves, what is the representation that our mind is using, and then how is it combining and manipulating that representation to get that final output, that final behavior. Excuse me. No. Oh. No, we're good on time. All right. So let's take an example of this approach, and we're going to take a look at letter recognition. So we're going to apply the things that we saw today, models, information in, information out, what goes on in between, that information processing approach, and the idea of different representations. And we're going to see how we can apply that to letter recognition, something that we know that we can do. So if I wanted to have a full explanation of letter recognition, the first thing that I would need to do, according to Marr's tri-level hypothesis, is figure out what we can do. So let's do that. We'll do a little experiment here. And what I'd like to do is everybody just call out the letter that you see when you see it, and we'll see if you can do some letter recognition.
R, F, Z, E.
All right, nice. Okay, so we know we can recognize those letters. That's part of our computational level understanding. We can recognize R, we can recognize F, Z, and P. Now the question is, how do we do that? Next level of analysis, what's the representations that we use in order for us to recognize that this is P? So how do we recognize the letter? Well, let's use R as an example. How do we recognize the letter R? So we'll look at one explanation. So this was one theory about how letter recognition worked, and it was known as the template model. And in the template model, the idea was that you have an external reality. You have R being projected onto a screen in the real world. And that external reality goes into an image processor. So right here is where the mind begins. All right, so right here is where our model of the mind is actually going to start. So the information coming in is the actual image of what was out there. And then that goes and gets compared to a template that is filled with different letters. So this is a template that you have in your mind. This is your representations of the external realities. And then a comparison is made, and then you end up with a decision. So when you see the letter R, and again, this is one possible explanation for how we do things. When you see the letter R, that goes into your image processor, and you have this image here. So right now, you don't know at this point. You have no idea what you're looking at. All you know is that you saw something. It goes into your image processor, and then you take what is in your image processor, and you compare it to your stored template. And what we're looking for is we're looking for an exact match. So you start off at the beginning of your template, and you say no, 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 no. Oh, wait a second. We got a match right there. And then you come up with your decision, and you say, yep, that is what we call an R. And this was one possible model for how it is that we represent our letter recognition strategy, right? We know we can recognize letters. Maybe this is the way that we do it, using these internal representations of an image processor, this template, and a decision processor for the output. All right, so that was one possible model. Another possible model used different representations. Specifically, it used demons in its representation of our mind. So these are not emotional demons. These are figurative, like actual little demons in your mind. And this was known as the Pandemonium Model. And this model was proposed by Selfridge back in 1959. And he proposed that when you see a letter, or when you see something in the external world, that gets sent to an image demon. All right, so again, right here is where the mind begins. So we got an image demon in our mind. Remember again that this is a model. All right, it does not mean that at the implementation phase, we actually have little, demons running around in our brain doing this type of cognition. But what it means is that the representational phase, our model of what's going on in our mind, is like a image demon. So we got an image demon, and that image demon sends this information up to a television screen that is in the corner of a room. And inside that room, we have a whole bunch of feature demons. And these feature demons have different little symbols on their bellies. So this one's got a vertical line on its belly. This one's got a curved line, forward slash, backslash. They have different features on their bellies. And when they see one of their features on the TV screen, they get really, really angry. They get very angry, very disturbed, and they need to tell somebody. And the people that they tell are the cognitive demons, and those are in the next room over. So the cognitive demons cannot see what's on this image over here, but they are going to be the ones that these feature demons communicate with, and they have different letters on their bellies, and they are the ones who eventually tell the decision demon which one of them has been complained to the most. And the last thing that we need to complete this model is the connections between the feature demons and the cognitive demons. Because not every feature demon talks to every single cognitive demon. So here we have the connections for the demon with the vertical slash. So he talks to R, he talks to P, and he talks to F, but he does not talk to Z. So when he gets on his phone and starts complaining, when he texts in his group chat, the people in his group chat are R, P, and F. for this feature daemon. The people in this feature daemons group chat are just R and P. Doesn't have F, doesn't have Z. This one over here is only connected to Z. This one over here is only connected to R. So those are the connections, and this is the Pandemonium model. So far, so good? Okay. So what happens when we see a letter? Well, that letter comes in, the image daemon sees it, and it gets on his belly, and the image daemon says, all right, I'm going to send this up to the TV. So it sends it to the TV, and then these cognitive daemons, remember, they get bothered, they get hot and bothered if they see something on their TV that matches what's on their belly. So this one looks and says, oh my gosh, I'm so angry. Look at that vertical line up there. And this one starts communicating with its group chat, and it starts sending messages. So F sees on their chat, oh my gosh, vertical line daemon, super angry right now. And P sees, oh my gosh, vertical line daemon, super angry right now. And R is like, oh my gosh, vertical line daemon, super angry right now. So it communicates with the cognitive daemons. This daemon over here, curved line, sees curved line up here. It says, oh my goodness, so hot and bothered. I got to tell my cognitive daemons. So it communicates with P, and it communicates with R as well. This one over here is like, I don't know what you guys are so angry about. I don't see anything with my belly up there, so I'm cool. I'm not going to tell anyone. But this one over here sees this this diagonal line right there, gets all hot and bothered, communicates to R as well. And then the final part of this is that these cognitive daemons up here will announce how many feature daemons they just got complaints from. So cognitive daemon R will say, wow, 3 feature daemons just sent me a message about how hot and bothered they are. Cognitive daemon P will say, only 2 of mine, reached out to me. Cognitive daemon F will say, oh, I just got the message from the one. And this last cognitive daemon Z is like, I don't even know that anything was even on the TV. Nobody's been calling me at all. And the decision daemon takes a look at who got called the most, and based on who got called the most, makes a decision that what we're looking at is an R. So that's the Pandemonium model. Any questions about that? All right. So let's take a step back again, and we'll take a look at, so these were actually 2 models that were proposed to try to explain how is it that humans can recognize different letters, right? How is it that humans can recognize the letters that we can recognize? So we got those 2 models. We got the Pandemonium model, we got the template model, and so far so good, they can both recognize R.
Do we still use those models as a way to understand cognition, or is that like something that's in the past?
One of them yes, the other one no. Yep. And we'll get to that right now. It's a good question, because we're going to take a look at some other things that we can do that let us know how we can recognize the letter R. So we're going to take a look at different fonts. So we're all familiar with different fonts. So let's take a look at whether or not we can recognize the following fonts. So once again, won't be too challenging. Just call it out when you see it.
R, F, C, P.
All right. Easy peasy, right? We can all recognize those. So this font goes into our computational level of understanding. Not only can we understand Arial, but we can also understand whatever this font was. We can understand different fonts. We can recognize letters even if they're not the same font. Yep.
In our mind or whatever, would cursive considered a different, like, a whole different thing? Because it's like...
I will get to that in just a moment.
Okay.
Yep, but it's a good question. So letter recognition. The quick answer is yes, but I will get back to a better answer to that. Because I think this will shed some light on that as well. All right, so we know we can do that with letter recognition. So we got the template model. Let's see what the template model can do with this particular font. So we have our input, once again, that goes into our image processor. Once again, that gets compared to our template of representations. And the key to the template model is that it has to match exactly the template that we have. That's the template model. It has to fit in like a puzzle piece into the template that we have represented. And then we make our decision. So in this case, when we have this font of R, that gets placed into our image processor. And then that image starts to get compared to things that are stored in our template model. And we start looking and we're like, no, 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 not a match, not a match, not a match, not a match. Well, what about that? Not a match, right? This is not this. This as a puzzle piece would not fit into there. So that would not be a match. No match, no match, no match, no match. And our decision is we have no idea what that letter is. So if our abilities did not include recognizing this as R, that would suggest that the template model is actually how we represent our letters. However, because we can recognize this font, but the template model says that we shouldn't be able to recognize this font, that's evidence that this is not the representation that we use in our minds. So the template model was abandoned. People tried to fix it a little bit. They're like, well, what if we have another template? What if we have another template? And basically it got to the point where they said, you're going to have to add like 500 million templates for every single font that we have. So they abandoned this because it just didn't support the behavior that we could do using this representation. Well, what about the Pandemonium model? So once again, we have the Pandemonium model. We got our image demon. We got our TV room filled with feature demons with different features on their bellies. We have the cognitive demons with the different letters on their bellies. We have our decision demon and all the connections between the feature demons and the cognitive demons. But again, specific connections. Not everybody is connected to everybody else. So what happens now when we have this image here? So that image gets processed. It goes onto the belly of the image demon. That gets projected up until the TV here. And then these feature demons start looking for their features in this image here. And notice that this image here, or this feature here, matches what that feature demon has. So even though, let me see, I won't go into too many kind of complexities of the model. But even if you have a slightly slanted line, you still have, well, I drew it horribly, sorry. Even if you have a slightly slanted line like that, you still have a lot of straight lines within that slanted line. So even though this is not a perfectly straight line, there are straight vertical lines in there, and that tips off this feature demon. He gets hot and bothered, and he makes his calls to his cognitive demons. This curve here, part of this curve here matches this curve here, so he gets hot and bothered, and he calls his cognitive demons. This over here, not shown anywhere here. This diagonal line here, again, wouldn't be in this portion, but it would be in this portion right here. So he would get hot and bothered, and he would start calling his cognitive demons. So once again, we have calls being made to the other cognitive demons, and then the cognitive demons just start reporting on how many of their feature demons have complained to them. R says he got complaints from 3. P says he got complaints from 2. F says only 1. Z still has no idea that anything's projected. And our decision demon says, all right, 3 is more than any other complaint number. It's got to be R that we're looking at. So this model here is better at explaining how it is that we recognize different fonts. This model here is more likely to be how we represent this information because it explains that we can see these different fonts. So interestingly, a couple of things about this model. Nobody really uses the demon model, the Pandemonium model of Selfridge, but the ideas that came forth from this model are still used. So the ideas of having features that are activated, and that these features only have connections to certain cognitive outputs. And then you have a decision maker that recognizes which output got activated the most. That kind of an idea is used. So in these days, in connectionist models, which we'll get into later on in the semester, these daemons here are replaced with what is called nodes. These phone lines here are replaced with connections. And basically with nodes and connections, you can explain how it is that we see letters and how we recognize letters. And also, interestingly, I told you previously that understanding how our mind works has actually made artificial intelligence and computer programmers better. Back in the day, let me just back up on this real quick. One of the really weird things about computer programming and artificial intelligence, and if you look at old science fiction, for example, they got everything about artificial intelligence wrong, because what they thought was going to be difficult turned out to be rather easy. What they thought was going to be easy turned out to be massively difficult, right? So things like speech, right? If you ever look at an old, sci-fi film, the speech it's either no speech, you just get little blinking lights, or it's like, I am a robot, how may I help you, right? It's horrible, right? Speech is actually not that difficult to do, and it's gotten really, really good, especially lately, where you can program a computer, to do speech very well. Although it was challenging for a long time. But give you a better example: letter recognition. Letter recognition was horrible for very long in computer programming because they were using a template model. And what do you do when your template model doesn't recognize a letter? You add another template. And then what do you do when that doesn't recognize another letter? You add another template. And then all of a sudden, you got 10,000 templates in your model. Well, that's great, but now it takes your computer 30 minutes to search through all the templates to find a single letter. So the ability to read, the ability to recognize letters, that was really, really difficult for the longest time. However, once these kind of ideas of connectionist programming and connectionist models started to pop up, once these ideas of nodes with different connections to different processors, eventually came up, and then all of a sudden the same kind of ideas started popping up in computer programming, and now it's very good at letter recognition. So back in, just 20 years ago, whenever you were signing up for something online, you did not have to click a little thing that says, I am not a robot, right? Because no robot had the ability to recognize, text, make those inferences, and put in their information. That was the easy thing to do, right? To recognize that text, right? They got to that point where they could recognize certain fonts. So what did they start to do? They started using those little CAPTCHAs, right? They started using those little, write what you have here, and there was a bunch of lines going through it and everything, and they found out that was very difficult for computers. As these models got more and more complicated, all of a sudden CAPTCHAs were no good because they were actually able to come up with enough feature daemons and enough connections where you can now computers can now recognize those CAPTCHAs. So what are they doing now? Now you have which one of these pictures contains a bird?
Those are kind of hard,
right?
not gonna lie.
Yeah, no, those are hard for us because what used to be, this was where our perception was, and this is where computer programming was. And now it's getting to the point where it's getting closer and closer and closer. And eventually it's just going to surpass our abilities. It already has in a lot of different ways. So very early on, addition, computer surpassed addition, no problem. That was simple, right? That was super easy to program. But other things that seem, and it's one of those paradoxes, things that seem easy for us massively difficult for a computer. Things that are difficult for us, massively easy for a computer. So computers were doing math, right? People struggle with math. Computers were doing math early. People struggle with physics problems. Computers were doing physics problems early. People can recognize faces easily. Just now, facial recognition is getting to the point where it's becoming close to where humans are. So, you know, in the future, it's going to be, you know, pick which one of these has a bird, and if you're successful, it'll be your computer, because no human could possibly do that. I don't know where they're going to go with it, but again, our understanding of how our human mind actually represents this helps to inform help to inform computer programming, and it leads to the AI that we have today. So, you know, cars that drive themselves. You know, it's the same kind of idea. They had a competition, it was like 15 years ago, right? Maybe 20, 15 years ago, where they asked the top universities to come up with a self-driving car. And they were going to drive in the desert. And it was if I can get into details, if I remember correctly, it was a 10-mile course, right? Where they would have to navigate around a boulder or two. They would have to stay on the road, not go into a sand dune. 10 miles, and whoever finished it the fastest was going to win the grant, and it was going to win, you know, the prize money. Nobody finished it. I think the furthest car made it like 500 feet before it got stuck. Now we got, you know, the Tesla self-driving cars. They're getting way, way better. And again, it's all part of understanding how our cognition works and influence a lot of artificial intelligence. All right. So letter recognition, just kind of wrap it up. What can we do? We can recognize our template model in the Pandemonium model. Says we can recognize R for the template model. Pandemonium model says, yes, we can recognize R. At this point, we can't tell the difference between these. Which representation might our mind actually be using? Can we recognize this R font? Yes, we can. So we can do this. Template model says, no, you can't do that. That immediately disqualifies the template model. That can't be the way that we recognize letters. Pandemonium model says, yes, we can. That makes it possible that that's the way that we represent letters. But again, we don't know right now for sure if that's a representation that we're actually using. All right, so again, the model suggests, I mentioned before that the model suggests questions that we should ask. So let's take a look at it now. So the Pandemonium model here, one of the questions that it can suggest is, will there be any confusion when you're looking at P? So this is a simplified version of the cognitive model, but what I want you to do for next class, this is a sort of exercise. This is a sort of, you know, let's make sure that we're understanding how this model works. Take a look at this model, and as it is, right, so they have a full version of this model that has all 26 letters represented. But as it is right now, what would happen if you saw a P? So if you saw the letter P and this was the model in your brain, what would happen? Would you get confused? And if you did, what letter would you be confused with? So that's one of the questions to ask. And that can have implications for people that have, for example, dyslexia, right? So people that do confuse letters. How can we understand which ones they confuse and which ones they don't? So again, a simplified model like this can help us ask the right questions to get to the heart of what's going on in our cognition. Another question we'll ask, and we'll take this up next class, what happens if we lose some connections due to brain trauma? What if you have a brain injury, right, and you lose some connections in your letter recognition system? What it's going to be, which are the letters that are going to be confused? What might occur? So will there be confusion when looking at R? So let's say that you sustained brain trauma and you lost this connection right there as a result of the brain trauma. So that demon here with the / now has no connection to anybody. At this point, which letter will R be confused with? So again, run through the model, try to do that analysis to figure out which one of those will now be confused. And again, it's a nice way to illustrate how having a simplified version, right? So nobody is saying this is what your brain is, or this is what your mind is like. But having a simplified version can help you ask the right questions that can shed insight into different aspects of for example, dyslexia, or for example, what happens after brain injury. All right, so any questions on anything we covered today? All right, so we got one last thing to do before we wrap up today, and that is to just make sure that everybody is aware of the first step, step one, in the social media professional development assignment number one. So again, this is an optional aspect of the course. This is just something that I believe is going to become more and more important, especially at this stage in your careers, to develop a social media presence, regardless of whether you're going on to grad school or whether you're going on to a job. Having a social media presence that basically says, yes, I am serious about this particular position, is a great asset to have. And also getting plugged into the community that you want to be a part of, to start knowing who the names are and start being recognized by some of the names, is also a great thing to have as well. So we're going to have very brief assignments. These will not take you more than a few minutes, at the most. But again, it's just a way that over the semester, we can help you build up this presence if you don't already have it. All right, so the assignment number one. First thing first, we're going to do this on Twitter. So that's the platform that we'll use. And the first thing that you need is to sign up for a professional Twitter account. And what I mean by professional account is that this is going to be the one that you use for professional purposes as opposed to personal purposes. So if you like to post stuff on Twitter, or if you already have a Twitter account and you've been posting things about your vacation, about your outfit of the day, about movies that you like, about whatever you might have been doing, that's great. Keep it, have it, don't change it, right? But get yourself a professional account that is focused in on psychology. So if you need to sign up, if you don't have one, the link here will take you to, it's, just in case, it's super simple, but if you don't already have one, this will give you a how-to for signing up for Twitter. So sign up for an account. They have tips for choosing a username. Choose a username that either is just your name, maybe has psychology in it, psycho or whatever, something that distinguishes it from maybe your personal account, something that lets people know this is what you're about. So sign up for Twitter if you don't have an account. If you already do have an account, you can actually have multiple accounts on Twitter. So I have my professional account and I have my personal account. So all my psychology work, the stuff that I do here as an educator, interesting articles that I've read, those all get posted on my Twitter account. My daughter's performance at the latest swim meet, that gets posted on my personal Twitter account. And the reason you want to do that is because when you start building followers, they're going to follow you for a particular purpose, right? So people that follow my professional account, they want to hear about the research that I'm doing on picture perception. They want to hear about, the approaches that I use, in my classes. As much as they probably would love my daughter, they don't want to hear about her second place finish in the individual medley, right? That's not something they want clogging up their feeds. So what you want to do is you want to make sure that if you do have a personal account, keep the two separate, right? So have one that's for profession, have one that's for personal. So if you already have an account, and you've already been posting personal stuff to it, have your professional account and set that one up and keep that separate. That one will be for psychology. So that's the first thing. Sign up for an account or a second account. And then when you do, send me your Twitter username via Canvas messages. So for some of you, it'll just be your name, maybe your name, 1482 or whatever it is. But for others of you, if you need to use a abbreviation, whatever, just to make it easy for me to track this, please send me your Twitter username just via Canvas messages. Just here's my username. That's what it is. So that's the second part of the assignment. Part number 3 is to follow me on Twitter. So find me at Palatinsane. That is the name of my my research lab. So follow me on Twitter. And then the last thing, because I will be posting stuff here that will basically I'll be assisting you on these from my Twitter account as well. So follow me on Twitter. And then finally, just to get you kind of plugged in your first kind of contact, I want you to follow one additional IUSB psychology professor on Twitter. So you can find ones that are on Twitter in two different ways. Number one, you can Google their name. Some of them are easier than others. So, for example, Dr. Rodriguez, he is one of the first Google searches that pops up. Day Bryant, Dr. Bryant, I don't know if she has a Twitter account, but it does not pop up because apparently there's a football player named Des Bryant.
Yeah.
And that is just, she might be on page 12 or something. So either Google their names if you can find their Twitter account, or you can simply just email them, go to the psychology directory, just email them and say, what's your username? I want to follow you on Twitter, and just let them know. So just one more. So you'll have two people that you follow, me and one additional psychology professor here at IUSB, and that'll be your beginning of getting plugged into that Twitter thing. So this is for points, and if you do want to do this, again, if you want to work on developing that, won't take too long. But this is the due date, Monday, January 14th by midnight. So again, sign up. If you need a separate account, get those separate accounts. Follow me at Polite and Sane, and find yourself one more psychology professor here at IUSB, and follow them as well. All right, other than that, we are done for today.
Yeah.